Hello, everybody. Today we're going to talk about hypothesis tests for the mean, but in this type of example, we're not going to have the population standard deviation. Instead, we're going to have the population sample standard deviation. Let's get into it. So we have this thing called the spotlight effect, which refers to the overestimating of the extent to which other people notice your appearance and behavior, especially when you commit a social faux pas. For example, we built a study where a student would wear a Justin Bieber shirt, I really meant that spelling, as they came into a lab class. In this experiment, the student would just sit down and quietly begin working. About 10 minutes later, the student would leave as the lab was busy doing their assignment. They'd switch into a different shirt and go on without the day. The professor would then ask this student, who was wearing the shirt, how many people they thought saw the shirt. We asked 36 students to do the same exact process in random classes. We found that on average, the students said 6.4 people reacted to the shirt with a standard deviation of 2.3. We also asked the students in the class at the end of each lab who say they saw the shirt the student came in with, and we found that on average, only about 3.1 students saw this shirt. All right, so is there evidence, ITE, at a 10% level of significance that the spotlight effect caused the average to be different? Well, first of all, how do I know this is a hypothesis test? Well, it's a hypothesis test because the standard way to ask for a hypothesis test is is there evidence? That's why it's a hypothesis test. Now, if I wanted a confidence interval, I would say build a confidence interval. I did not ask that. I want to make that very clear. I asked, is there evidence? And typically when we ask, is there evidence, I want to go through the steps of the hypothesis test. And that's what I'm going to do here. So let's open up and I believe those are at the beginning in case we have to remember, no, not in the, where did we put them? Right there they are. Steps in the hypothesis test. And step 1, hypothesis test. Understand the problem. Understand what we're dealing with. Understand the data. That way, in step 2, we can get right into it, state our H0, H1, alpha, and really state all the rest of the data that I have. And that's what I'm actually going to get right into, is in my question, can I determine the H0 quickly, the H1, the alpha, and once I've done that, can I determine which test I want to use? What do I mean by that? Well, let's go through this carefully. So in the first part of the process, I need my H0 and my H1. The H0 is your no. So let's go back. What is the traditional opinion here? Well, it says it here that at a level of significance, the spotlight effect caused the average to be different. What do you mean by cause the average to be different? Well, what we have is we have the student's average versus the class's average. And we're wondering, is there that much of a difference between them? Again, we have the class's average, which we'll take as our national average, our norm. That is the classroom. About 3.1 students recognize it. The students would be the sample. The students that actually did the procedure, wore the shirt, would be our sample. So we're looking at the national, quote unquote, the national average, which in this case would be the class average, versus the sample of students that walked in and left from the labs with this very special shirt on. So to me, this is the national average. That is, mu is 3.1. And so we have mu is equal to 3.1. Notice I'm using mu because we're looking at an average. If this was proportion in a later video, I'll use pi for proportion. But because this is average, I'm utilizing mu. And that would be 3.1 people if you're looking at units. Now we're looking for whether this is just a difference test. That is, we don't know if it's more or less. We just believe it's different from. That's very important to me, is that this is a not equal to two-tailed test. How do I know? Go back to the question. It says, has the spotlight effect caused the average to be different? And that's the key. To be different. It didn't mean greater than, and it didn't mean less than. It means different from. Different from is a not equal to test. All right, so what's our alpha? That's the level of significance, and that's 0.1. That's the first thing I'll put up there. My alpha is 0.1, 10%. All right, And yes, we have to be very good at writing our alphas and our p-values in decimal form. So the alpha is 10%, the level of significance. Got to be given in the question. From here, now that you know it's an average test, we can go to the formula sheet. And let me bring that up. At any time, again, I would say pause the video, take a picture of things that you need, and then continue. So I'm looking at a hypothesis test for average. All right, we're looking at average time, how many people on average would look at this t-shirt, the spotlight effect. We also have to check in. Do I know the sample population? Is that known? Standard deviation, SD. Do I know the sample population standard deviation? Do I know, and I could flip back to the previous formula, do I know the population standard deviation? That's going to be key. Which one do I know? And let's read. So we go back to the question. It said right down here, the only standard deviation I have, it said we asked 36 students, and that's my sample. We asked 36 students, and 6.4 people they guessed were checking them out on average. And the standard deviation of this group of 36 students, the standard deviation was 2.3. So this number did not come from the class. It came from the 36 students I sent into random classes to see if people would look at their t-shirt. And so that's why that is S. So let me just verify a couple letters here. N, X bar, S, and mu. Well, mu is the population average. In this case, again, I'm treating the class as my population average. Every single class I ask, hey, how many people noticed the shirt? And that is, we'll call that quote unquote the population average. X bar would be the sample average. Well, what's my sample? My students, my 36 students, and by the way, that would be N, right? Sample size. My 36 students, I'd have them go into a lab, different classes, all right? I had them walk in, I had them walk out, and then I asked them, hey, how many people think you saw your t-shirt? They'd give me a number, a whole number, like 6, 8, 5, 4. I collected all that data, then I averaged it out, and I found 6.4 people on average they perceived. This is the sample they perceived. The classroom saw this. The sample perceived this. And then there's a standard deviation, 2.3, by the sample. How do I know it's the sample? I read. 36 students, that's the sample, and that's the standard deviation of the sample. That's how the English sentence structure works. So that's why I have S. That's very important. Since I have S, I will be utilizing the T distribution. That's very important to me. When you have a sample standard deviation, you'll be utilizing the T distribution. Got it. So all this data would be the data that I would collect in my list here. I would list my data, all right? What I just did in Excel, I would list it all down. My X bar, my mu, my S, my N. I'd list down the important data values. Got it. From here, now what's my steps in my test? I like to make sure I follow the steps so you guys are ready for them. So we have H0, H1, and alpha. It's time to create the critical region now, and then the test statistic. Got it. So we need to create the critical region. So, time for the critical region. To build the critical region, it's a good thing we're doing the T statistic, so we know how to draw the T distribution. It looks roughly like the normal because it's a cousin of the normal. Which T distribution are we drawing? Well, let's review that. The T distribution is based off of what? N, the sample size. In this question, our sample size was 36, which means our T distribution is based off of 35 degrees of freedom. So this is the T35 curve, because the degrees of freedom is always n minus 1. And recall, to find the particular T curve, because there are infinite number of T curves, you need to know the degrees of freedom. If you have issues on the T curve, please look back at my videos on the basics of the T distribution. So here's our T distribution. So what do I want to do? I want to do a hypothesis test. Well, I know it's a not equal to, and let me check out alpha. Recall that both of these pieces right here help me build my critical region. All right? The not equal to means I'm going to have 2 bars. Boom. The alpha is the allowed area on the outsides. So since it's 10%, and this picture is symmetric, I'm allowing 5% on both sides. That's very important to me. Not equal to means two-sided test, and alpha gets shared to both sides, so a total of 5%. This picture means if my data value falls into here, I do not reject H0. There's not enough evidence to reject H0. If my data falls into here, I'll clearly reject H0. And that's what it's always about. Remember, you only have two conclusions. Either you're going to reject H0 because you have statistical evidence, or you're not going to reject H0 because you don't have enough evidence to get into the rejection regions. That's why it's called the critical regions. These are the critical regions. So it all comes down to, bottom line, this t-value. Finding this t-value that bounds the critical regions. How does one find the associated critical values for the t-value? Well, the good news, if you followed in previous videos, you know t-values can either be found in the table, all right, in the t-tables, or you can utilize a program like Excel. And so we have t.inverse. T.inverse will find us our critical values. You just got to know how to utilize t.inverse. All right, let's go to Excel to figure this out. So instead of calling it t, I'm going to call them the critical values. I apologize. I was going to go to the Tstat faster, but instead I'm going to go to the critical values. So how does one find the critical values? Well, you're going to use t.inverse. And again, at any time you're confused, you should pause the video, play it again. T-inverse. What is it asking for? Well, it's asking for probability below. That's how T-inverse works, or norm S-inverse works. T.inverse works with you tell me the probability below. So you got to go back to that picture and think about this picture. I'm looking for a very particular bar, this bar. What is the area or probability below that bar? Well, if it's 5% is above it, then that means 95% is below it. And that's the number I'm going to plug into T-inverse, 0.95. Of course, my degrees of freedom is n minus 1, so 35. And that's how I get my critical value of 1.689 or 1.69 for rounding purposes. So I know my critical value, first of all, 0.95, comma, degrees of freedom, 35, and that is 1.69 to 2 decimals. Please make sure you go to the right number decimals you need. In this case, I'm using 2 decimals, 1.69. Let me highlight the code again so you can pause it if you want to take a look at it. I am using t.inverse. The t, for the obvious reason, is the t-curve. The inverse because that's how you find critical values. If you tell me the area below the critical value, I'll find the t-value. In that case, the critical value here is 1.69. It all comes down to the picture. That's why I always draw the pictures here. The critical region, all right? How do I find this bar? I need to know the area below it. The area below this is 95% because the area above is 5. And 5 and 95 add up to 100%. That's why I plug 95% in. Why 35? Because that's the degrees of freedom. I need to find the particular t-curve to do the advanced calculus on. Thank you, Excel, for doing the advanced calculus. Now I can find the t-value. And yes, that would be negative 1.69 to be a complete lecture. Negative 169, positive 169. Awesome. So now I have my critical values. Now it comes down to, what is your test statistic? What is your actual test statistic? Well, the test statistic by our formula sheet is right here. Is our mean, our sample mean, minus the mu divided by the standard error. Standard error would be S over radical n. So my formula, in this case, is my average, X bar or M, whatever choice you want to use. I use X bar most of the time, but I also use the letter M. So X bar or M for the mean, your sample mean, minus the national statistic, or in this case, the classroom statistic, divided by the square root or standard error divided by the square root of sample size. So we need to find our test statistic. So how does one do that? I call Excel into action. It's just a calculator number. It is what? It is, once again, my sample size. Got it. How close is it to the national number? The national number, which is a classroom number, is 3.1. Then we ratio it to get a perfect unit, the Tstat unit that has no units on it. It's not people, it's not dollars, it's not cents. It's just a number that represents position, the Tstat does. How do I get that ratio? Well, it'll be S, sample standard deviation, divided by the square root of N, sample size. And again, the cool thing, let me hit enter here, the cool thing about writing these codes is once you write these codes once, you can copy and paste these codes forever. And so what I have here, again, I would pause the video to make sure it makes sense, the formula. And then you can continue on. We have x bar minus mu, check, divided by the ratio, the standard error. Please notice our Tstat is ridiculous. All right, it is very huge. I know as soon as I get above a 2 or below a -2, I have something special. If I get above a 3 or a -3 in the T value, I know I got something highly special. When you get to an 8, something is huge going on. Well, look at it. The classroom average, roughly 3 people noticed the person with the Justin Bieber shirt. In that person's opinion, they're like, whoa, whoa, people are watching me. People are really, really looking at me. Welcome to, again, the topic called spotlighting. People often have a higher perception of themselves than, in fact, what's going on. And that's exactly what's going on here. It's almost doubled the perception. And that's why the Tstat was so huge. 8.61 was my Tstat when I do the math out. As soon as I know that number, I know exactly what's happening, but let's finish it off because we want to make a conclusion now. All right, and my conclusion, let's check it out, is based off, this is your number, your sample. How does it fit into the picture? Well, think about this, 8.61. It completely blows away our cutoff of 169. 8.61 is so far off the chart, it is not funny. It is well within the rejection region. And so conclusion, I reject H naught. Great. What the heck does that mean? You should always have, language that follows up the math. I reject H naught. That's awesome. Why? Well, because my Tstat is in the rejection region built by calculus. Here's my statistic. Here's the bar 1.69 put down by calculus. How does it put down? It was put down by alpha. Everything comes together. Alpha not equal to build your rejection regions. That's the calculus. This is your sample, the green bar. Your green bar is clearly in the rejection region. What are you rejecting though? Let's go back to the beginning. I assumed 3.1 people is the national average. All right. Is my perception different than the national average? Heck yes. My perception is clearly the perception of the student is clearly different than mu, the national average. And I shouldn't even write mu. I should write the classroom average of 3.1. And hence, the definition of the spotlight effect, when somebody creates a faux pas. Cool. And some would say, we're done. I agree. Some would say, you are done. But depending on your professor, or depending on what you're trying to do in research, you may have to check it. And so there are a few more steps I call in my hypothesis test. We are actually done. We've done it. We've rejected. We have evidence right here. This is my statistic, and it clearly falls in the rejection region. I want you to understand, you are done in a classical rejection region hypothesis test. I am making sure that when you go on in other classes, other grad school classes, you have all the weapons at your disposal. What's your next weapon? Compute the p-value. Some people love doing the p-value and then make a statistical decision. So here we are. Compute the p-value. What is that? Well, it's an alternative to the critical region. Some people don't like the critical region because it's based on alpha. Some people just want to base everything based on the p-value. How does one do that? Well, you draw your picture, and you put your statistic down. My statistic, my number was 8.61. Well, you still have a two-sided test, so that's negative 8.61. And by definition, please, let me pause. We have a two-sided test. That doesn't go away. We're still doing a two-sided test. That's why there's 2 bars. Two-sided test means 2 bars. The not equal to tells me the two-sided test. The p-value by definition is the area outside of your sample. That's the p-value. The area outside of your sample. So in this case, my sample was 8.61. I want to know what is the probability I can redo this study and find a sample that has even more extreme value. To do that, I need to calculate this area. Well, because it's two-sided, I know I'm going to double something. That's where the 2 comes in. The 2 comes in because I have 2 sides. If I have a one-sided test, I would not multiply by 2. Because there's 2 sides, I'm multiplying by 2. I will use the t-curve because, guys, it's a t-curve. Dot dist. Whenever somebody wants a p-value, it is the dot dist I use. All right, t dot dist is built for the p-value. So let me go back to my Excel sheet, or in this example, and let me bring out the p-value. So to find the p-value, I know I'm going to go 2 times something. And I need to understand t.dist. I like to run through the code to make sure I understand what's going on. So t.dist needs 3 numbers. It needs to know the bar in the sand, the degrees of freedom for the curve, and whether you want cumulative. In hypothesis tests, you almost always want cumulative. In basic stats, you always want cumulative. So there always will be a 1 at the third one. The t-value, we got to be careful here because the way I did this. And what do you mean, why do I got to be careful? Well, let me not put the 2 in here. Let me just find the t... I'm trying to think of how I want to call this. The probability below. All right. I got the t-stat, okay? The t-stat below. I'm trying to be very clear. I've done this many times, but I want to make it very clear what I'm trying to do. I need to get to the p-value. I need to think about the number that's going to pop up here when I use t.dist. See, I'm going to use t.dist on my test statistic right there. That's the idea. There's my test statistic. I'm going to do t-stat. So I'm going to do t.dist on the test statistic. My degrees of freedom is 35. We know that. Degrees of freedom is n-1. I always do cumulative, period, when I'm doing basic statistics. Click. Holy moly, it's 100. It's 100%. No, it's not 100%, but Excel has given up. We might be able to pop up a bunch more decimals here until it finally cracks. So it finally cracked, but look at that. It's 99 point, holy moly, a bunch of 9s before it gets to anything less than 100%. And why is that? Well, because we have a t-stat of 8.6. My picture is kind of really bad because what's going on is 8.6 is so far from center, it's not funny. And so what we're saying is the t-dist, I need to make this very clear. The t-dist gives you the area below, okay? The t-dist gives you the area below. And what you have is practically 100% of us fall below a t-value of 8.61. And I agree to that. Almost everybody falls below an 8.61. Not everybody, but it's so darn close, you might as well say 100% of us fall below that. All right? But that's not what we wanted. Right, guys? We didn't want that green shaded region. T.dist gives you the area below. That's the idea. I don't want that. I want that red region. And in fact, I want to double that red region. This was kind of weird because of the 8, but I'm trying to keep it fluid. I know that 100% falls below. So what falls above would be 1 minus. And then if I want to double, I would double it. So again, if I know what's below and t-dist gives me below, I could take 1 minus to get above it and then double it. So my formula here is actually incorrect. My formula, if I want to be perfect, will be twice 1 minus t dot dist. And that's the actual p-value. That's my actual p-value. Twice because I have two sides that are symmetric. Why 1 minus? Because t-dist gives me below. So if I want the area above, I got to do 1 minus. And then twice it. And so that's the actual code for the p-value in Excel. But I want to be very clear on what t-dist gives so you understand why my code will be 2 times parentheses 1 minus, and since I already found the t-dist below, I'm just going to do 1 minus that number. And yeah, it's ridiculously small. It's not 0, but it might as well say it's 0, all right? Because we're talking that many decimal places. E-10 represents a very, very small number in Excel, okay? We got a lot of decimals, 10 decimal places before you see the 3. So it's a very small number for the p-value. All right, guys, let's go back to our paperwork here. Sorry, I'm jumping all over the place for no reason. So our p-value, you might as well say it's 0%. All right, it's roughly 0%. So what does that mean? Well, p-value less than alpha implies reject. That's our statement. If your p-value is less than alpha, you must reject H naught. And honestly, your p-value is 0. It's less than any alpha anybody throws at me. Well, what if your alpha's 10? Who cares? Alpha's 5%. Don't care. Alpha's 1%. I don't care. My p-value is 0%. Throw any alpha you want at this. So this p-value does not care. It's not sensitive to alpha. That's my fancy word. My p-value is not sensitive to alpha. You can give me any alpha and I will blow it away. My p-value is under any alpha. Now in this case the alpha was 10% if you go way back up. So 0 is clearly less than our alpha given of 10%. But I want to make it clear that I don't give a crap what alpha they give me. I'm rejecting because my p-value is so under any alpha that I will reject. And what does that mean again? Well, again, that means I believe the student's perception is very different than the class average. That's what it truly means. So you once again say your blah. You would say your end in speech. Given the p-value approach, my p-value is underneath any alpha somebody gives me, 1%, 5%, 10%, which means I reject H naught. What that means is the student's perception is clearly well over what the classroom perception is of that t-shirt. Awesome. And so we've done 2 types of tests here, the critical value test and the p-value test. Both are awesome tests. I like to run both because they should check each other. If one rejects, the other should reject. If one does not reject, the other should not reject. All right? So they both should say the same thing. If they don't, you've done something poor in the algebra. All right. So here's the cool thing. You've rejected. So this gives me a chance to be that teacher moment. You've rejected. What does that mean? That means in the student's mind, the average is not 3.1. In the student's mind, the average is somewhere big time higher. So in the student's minds, there's a confidence interval that's around them that they feel is bigger. Can we build that confidence interval? And yes, you would only build it if we reject. So if reject H naught, we typically build a confidence interval. Which one? Well, you go back to your alpha. In this case, the 2-sided test was about 2-sided with alpha 10%, which means I would probably build a 90% CI. That's what I would build. Because your alpha on the 2-sided test was 10%. That means inside you had 90% confidence. So that's the confidence interval I would build. So how does one build a 90% confidence interval? Well, you go back to my lecture on confidence intervals. All right, or you can go to the formula sheet and the confidence interval built for the t-distribution, if you follow it in order, is right here. It is the sample mean plus or minus a particular t-value times S sub m. S sub m is right here, and mean is your sample. The confidence interval, by the way, is truly based off of your sample. So what we have here if I want to build a confidence interval, is, once again, let me just write it down. The confidence interval to capturing the true mu. And that's what you're trying to do. You're trying to capture the true average. You don't believe the average is 3.1, at least the student doesn't. The student believes it's way higher than that. Can we capture an idea of the student's perception? Of course we can. What we can do is use the student's average and then plus or minus an error. What is the error? It's t times s over radical n. Well, you know three of the numbers, x bar, s, and n. Those are based on your sample. X bar, s, and n are based on your sample. The t is based on the confidence level you want to showcase. In this case, the confidence level you want to showcase is 90%. And since it's a 90% confidence level with a sample size giving me degrees of freedom of 35, I know how to find the t value. The confidence level goes inside. Degrees of freedom picks the particular t curve, and I can find my t value. How would you find it? You would use the critical value as nothing more than t dot inverse. What does t dot inverse need? It needs the area below the t value you're looking for. Think about the area below here. Not 90, but 95% is the area below that bar. I'm looking for that bar. What t value represents that bar? And since the area below that is 95%, I'm going to look up 0.95 degrees of freedom. And I apologize. Degrees of freedom is clearly 35. You see that. I see that. 35. And so that would be the critical value for this right there. That's the t value I'm looking for. I know n, x bar, and s. That's from my sample. N, x bar, and s come from my sample. T comes from the confidence interval you want to build. You want to build a 90% confidence interval? That builds this picture. I often draw pictures to understand what I'm doing. So double bar, because a confidence interval always has two bars, by the way. And I wanted a 90% confidence, which means 95% area below, and that's what I'm utilizing to build my confidence interval. All right. So I want a 90% CI. So a 90% CI, the first thing I need to find is my t value, and that's going to be found by t dot inverse. T dot inverse finds the confidence interval values, okay, guys? What I would do on a cheat sheet is just write down where the codes are useful. Notice I'm bouncing between t dot inverse and t dot dist. All you got to do is pause my video and notice when I put the codes in, because they're always the same. If I want to build a confidence interval, utilizing the t is t dot inverse. The key to the whole gosh darn thing is knowing how much area is below that top bar. That you have to think about. Degrees of freedom you also have to think about, but that's n minus 1. It's a formula. It's n minus 1, so 35. And yes, my t critical value is 1689. If you're clever enough, yes, it matches up here. I know that. But that's higher level thinking of how hypothesis test and confidence intervals link together. If I'm building a confidence interval, I'm going to have to build the error so I can build the upper bound. And I should say not the upper bound. I'm going to do the lower bound first. I'm going to give myself some space here. Then I'm going to build the upper bound. So what is the error? The error is the back end of the confidence interval, okay? Now that I have the t, I can build the back end of the confidence interval. The back end of the confidence interval is t times s over the square root of n. Our n here would be that. And so there's my margin of error, 0.63 points. Again, the margin of error is the back part of this formula, and that's what I found. The error E is the back part of the formula. So I know my confidence interval will be x bar plus or minus this error. And that's what I'm going to do in Excel. So I want to find the lower bound. The lower bound would be the average x bar, that's why I label everything, minus the error. The upper bound will be the average, your sample average. Make that very clear. Your sample average. You build a confidence interval based on your information, not the national information you don't believe in anymore, right? You just rejected the national number you don't believe is 3.1. So you're trying to build a confidence interval based on your belief, based on your perception, the spotlight. And so, sorry, I put a minus there. I want a plus. The upper bound is your average plus a little bit of error because you based your numbers on a sample. And there it is. There is your confidence interval. I'm 90% confident the person running the whole test, right? The student, their perception is somewhere between 575 and 7 students noticed them. That is the 90% CI. So the 90% CI is mu is between the national average, mu, the classroom average is somewhere between those two numbers. On the low end, it's 5.75 students. And on the high end, it's 7.05 students. That is the student's perception. They believe the national average is between those two. That's what my study shows, is that the student's perception, there is a 90% belief, a 90% confident that the student perception of the national average, the number of people that look at them, is somewhere between 5.75 and 7.05. To me, this is my third check. Notice what number is not between those two. That is the actual perception of 3.1, I believe. We go way back up. The norm, the national number, was 3.1. A third check is 3.1 in this confidence interval I've been building. 3.1 is not in here. 3.1 is well below this confidence interval. To me, it's my third check. If I reject, my statistic should not be between the low bound and the high bound. Again, in the student's perception in the spotlight effect, they believe at the low end 5.75 and at the high end 7.05. They believe with 90% confidence that that's the true number actually looked at them. We know the national number is 3.1, but in the student's perception, it's somewhere between there. Hence, it's a third check. I've rejected because my sample statistic is above the critical value. Reject 1. Reject 2. My p-value is well under alpha. Reject 2. Rejection 3. Here's the confidence interval the students believe. That's the student's belief in the confidence interval. The actual belief was 3.1. That is not in that confidence interval, so that's another reason to reject. So that's 3 times in a row I have rejected. I think that's enough to tell you there's clearly some type of spotlighting effect, some type of psychological phenomenon going on when people wear a shirt that they believe is a faux pas. That's really what's going on there. All right, guys, let's make sure I've done all the steps. So we built an appropriate confidence interval. We did that. And now we need a summary conclusion. All right, well, let's do that one more time, the summary conclusion. What I would do, I'd state 3 things. First, I reject H0. That's my first statement. Why do I reject H0? Well, here it comes. My Tstat is bigger than the critical value. That's a critical value approach, so I reject. Number 2, my p-value is smaller than any alpha. My p-value is 0, roughly. It's less than any alpha, even this 10% you gave me, so I reject there. And third, my mu is not in this confidence interval based on my sample. My mu is not in the confidence interval based on my sample. So something unique is going on in my sample. And so that's what's going on. It's the sample belief. So bottom line, all right, my belief, the belief of the student is definitely different than the base number. So there's something going on when somebody makes a social faux pas of wearing a weird t-shirt, a weird hat, maybe they got a different type of haircut, something they believe that's a social faux pas, okay, and their perception is clearly higher than the national norm that we sampled from all the students in that classroom. That's called the spotlight effect. Awesome. And that is part A. All right, let's look at part B quickly. What if we change our level to 5%? I've already discussed that. If we change our level significance to 5%, I don't care. I still reject because my p-value is 0. Since my p-value is 0, I know the answer for part B. You want the answer? I still reject H naught since p-value is 0%. Bottom line, I don't care what level significance you change it to. And the typical level significance you give me are 1, 5, and 10%. 1%, 5%, and 10%. Those are your level significance people usually take. I don't care which one of those three you pick. 0%, that is my p-value, beats all three. That is smaller than all of them, which means I will reject no matter which level significance you throw at me. 1%, 5%, or 10%. Awesome. All right, what else we got here? What if we change it from a different than to a greater than as our alternative? Well, that's a good question. If we change it, the alternative to a greater than test, right? We have the alternative as a not equal to. What if we have a greater than test? That would be a one-sided test. A greater than test would be a one-sided test. Well, the alpha doesn't change. Alpha's 0.1. The only difference, let's think about this. So let's put on our high-level thinking hat. We're switching it to a greater than test. What does that mean? Well, what that means is, again, the national norm is 3.1. We are inspecting the greater than test. All right, the greater than test. We believe, and so in this case, there's belief that the spotlighting effect is over the average. It's overestimating. That's really what it is. We're not doing the not equal to. We're just going to go straight up and say, we believe using the spotlight effect that it's going to be over 3.1. We truly believe that. Well, because my critical region is based off of that, I now know I only have one bar for my critical region. That's the key. And all 10% is going to be shoved into this one bar. All 10%. Recall, alpha still 10%. We haven't changed alpha. This is really the biggest difference, is how you build the picture. My critical region, okay, my critical region only has one bar because of the greater than symbol. The greater than symbol means use the top bar. If that was a less than symbol, I'd do the bottom bar. A greater than symbol represents use the top bar. Got it. So I have to find a different t value now, a different t critical value. And how do I do that? T dot inverse, that's how you find critical values. You need to know the area below. Look at your picture. If the area above is 10%, then the area below is 90%. I still need the degrees of freedom to calculate it out. So here we go. Let's find that critical value. So over here, alpha is still 0.1. N hasn't changed. It's 36. X bar hasn't changed. S hasn't changed. Mu hasn't changed. Critical value, that definitely has changed. You are now doing a one-sided test. Since it's a one-sided test, I have to put all area below that, so 0.9 now. Degrees of freedom hasn't changed. It's 35. And so that is my t critical value. My t stat hasn't changed though, right? My t stat has nothing to do with the critical value. My sample is still my sample. It's still 8.61 to 2 decimals. Just look over there, I just rounded it. Notice, in the critical value approach, the only thing that's changed is the critical value. That's the only thing that changed. And notice my critical value got smaller. Well, that makes sense. My critical value is going to get smaller when I have more area underneath it. All right? Less area underneath means my critical value gets smaller. More area underneath it, my critical value gets larger. I have less area underneath it now. 0.9 area underneath it. So my critical value got smaller. Well, that's all I need to know. My critical value got smaller, but my test statistic remained the same. I am still rejecting. All right? I am still rejecting. And that's what I'll say. Even though my critical value has changed, I'm still rejecting. So, my T critical value, 1.31, is that. So I'm going to clearly, I reject H naught. The reason being is my statistic is in the critical region. My statistic, right, my test statistic, the one I calculated out, is 8.61. My statistic is in the critical region. And that's why you reject. I'd expect you to write this up all pretty, draw a pretty picture, do all the details. I'm just kind of going through quicker because we've done the bitter details in the first example. You would still write your hypotheses. You would still write your alpha, n, and all the numbers. You draw your pretty picture to get your critical region. Your number for the critical region was 1.31 based on this picture I drew. My test statistic is still an 8.61. An 8.61 falls way up here. My test statistic falls way up there. And so the answer, well, there's your answer. If I do the critical value approach. All right, if I just stop at the critical value approach, what if we change from different from to greater than? If I change from different from to greater than, I still reject because my statistic is still in the critical region. All right, my statistic is still in the critical region, which means I still reject. All right, I can still find the p-value if you want to continue on. So how does one find the p-value when we're looking at a one-tailed test? That's very important. This is a one-tailed test. So let's think about it. My statistic, 8.61. It's a one-tailed test. So the only difference here is I'm still going to do 1 minus because I want the area above my statistic. But I'm not going to multiply by 2. I will not multiply by 2. I will multiply by 2 if it's a two-sided test, a not equal to test. Because it's a one-sided test, I don't need both sides. I only have one side. So I want a sample more extreme. They better be more on the positive side extreme, not a double, okay? That's the difference. It's a clever little difference. Two-sided test means I double the area. One-sided test means I do not double the area. Cool. Now, I should have put 90% confidence above that. 90% CI. This one, I do reject, which means I should build a confidence. But you got to be careful here. That 10% went outside the greater than. In a confidence interval, you usually have 2. Okay? You usually have 2 things in a confidence interval. So you usually have 2 bars, that is, 2 sides. And if one side has 10%, the other side must have 10%. So you're actually building the 80% CI. I don't like that. What I usually tell people is to build a confidence interval that they want. So in this case, let's say we want a 95% CI confidence interval. I don't like the idea of an 80% confidence interval. That doesn't sound that much confidence. I'd rather see a 90, 95, or 99. Who determines that? Your research does. 95 is usually the one everybody goes to. So how do you build a 95% confidence interval? Well, you go back to the previous setting. All right. You know you have X bar and an S. You have that. All you're missing is the T critical value for the confidence interval. All right. That's what you're missing. So if I want to build a 95% confidence interval, I would draw me a picture. Confidence interval has 2 bars. I want 95% in the middle. The T is the T right there. If I want a confidence interval T, I would use T dot inverse. If you're using T dot inverse, you need the area below. The area below would be not 0.975 degrees of freedom, of course. Why is it 0.975, guys? That's the idea. Why is it 0.975? And I can't remind you enough, you need to know the area below the bar if you want to find the bar. The area below that bar is 97.5 because the area above here is 0.025. That's why. Now I'll let you think about that, why that is. 2.5, 2.5, make 5. 95 is in the middle. 95 in the middle leaves 5 on both sides divided by 2. So 2.5. So this is 975. And that's what I'm going to put in Excel. Equals T dot inverse. Again, the only time I use T dot dist is when I'm doing the p-value. Other than that, I'm using T dot inverse, okay? T dot inverse finds my critical values, my critical edges in the confidence interval. And just getting used to the code. And I would write down in your own words, all right? Write in your own words how you find each piece. How did I know to use T dot inverse? Because T dot inverse finds the critical bars for the confidence intervals. Now, I do need to know how much area is underneath. That is 975. That you just got to learn. Degrees of freedom is a formula, n minus 1. That's no big deal. And so there it is. From there, I can build my confidence interval. First, I need the error. Well, the error will be T times S divided by the square root of n. Boom. And then the lower bound will be the center, your sample center, of course, again, minus the error. And then the upper bound will be the center, your sample. Confidence intervals are always built off of your sample, not the national number. Confidence intervals are always built on samples, okay? Never mu. So your sample is x bar plus my error. So once again, I need to know the t value that builds the confidence interval, and that's the 203 here. Then I need to create the error, which is the back end of the confidence interval, which is T times S divided by radical n in the formula. From there is just basic algebra, adding and subtracting, subtracting and adding the average from there. That is the sample average. I can't state that enough. And there it is, my confidence interval. Once again, I'm 95% confident that the true average number of people looking at me when I wear a weird shirt would be 5.6 to 7.1. Clearly, again, my perception is off. 3.1 is the national number, the actual number the class saw. This is my perception. Gotta understand the question. This is my perception. This is what the classroom actually saw on average. 3.1 people actually paid enough attention to your t-shirt. I felt this number. This number's not in the confidence interval, which tells you something is different, something is unique. And all three should line up one more time, right? My statistic is over the critical value. That's why I reject H naught. My p-value is less than alpha. That's why I reject H naught. My mu is not in the confidence interval. That's why I reject. All this leads to perception is more powerful than what actually is happening. That's really what it ends up saying. All right, guys. I mean, there are a few other things you could do here, right, in the steps. You could check the assumptions, and you could do the Cohens D if you care. In this case, we could easily check the assumptions because our sample size, right, central limit theorem gives normal. Woo woo! That's awesome. The central limit theorem says if your sample size is over 30, we definitely have normality in all samples, okay? In the samples, the distribution is normal. I don't know what the distribution is for number of people watching a t-shirt. I don't know that, don't care about that. I know the sampling distribution will be roughly normal, and since I'm dealing with the samples, that's what I'm looking at. If I want the population of just looking at t-shirts, that's something totally different. I'm looking at sampling distributions. And when I collect all samples of 36, those would be roughly normal. That's the idea there for the central limit theorem. So I checked my assumption. And yes, that should be checked right away. What other assumptions do I have? Well, let's go over here. I have a single sample for mean, and I do not have the population standard deviation. So first, I should check about the random sample. Did you make sure this is random and representative? Well, it's a textbook question, so yeah, I gotta believe it is. If you're collecting data, you better collect it randomly and representatively. You better do that. Normality is easy to check for all of us, and that's just making sure it's over 30. Now, wait a minute. What if the number's under 30? Well, it could be. If it was 25 people, you just better know something about the original distribution of what you're studying. If the original distribution was normal or roughly normal, then yeah, you can do whatever sample size you like. Small is fine. But if you have no clue about the distribution, the real distribution, then you better sample over 30 to guarantee the normality. That's all, guys. Over and over, we're going to come back to the central limit theorem and how useful it is. Can we do the Cohens D? We could do the Cohens D here. All right, not all the time are we asked to do these. That's why they're called extras. But sometimes, depending on your research, you might need to do these extras. And it's always good to know how to do the extras, because to some people, the extras are the most important part. So what is Cohens D? Well, Cohens D is a measure of how significant the sample size is. That's what Cohens D is, okay, guys? Cohens D is, first of all, the formula. Cohens D for this one is mean minus mu over S. That's the Cohens D measure in this case. Mean minus mu over S. Notice it is X bar minus mu over S. Notice the formula does not have the sample size. Well, Cohens D is all about, do you think sample size had an effect on my answer? Some people might say that. They might try to call you on and say, no, you have blah, blah sample size. That's what's causing the answer. That's what's causing you to reject or not reject. Well, I want to make sure sample size does not have a big effect on my results. So I can completely kill the sample size in my formula, and that would be Cohens D measure. So let's go check that out in Excel. I use Excel as a calculator, if you haven't noticed in my videos. Excel to me is a calculator. So I could have added it, and I'm going to add it now, into my regimen here. I could calculate out the Cohens D. Well, the Cohens D by formula is X bar minus the national number divided by just the standard deviation. And that's the Cohens D. All right, Cohens D is, no, we're not going to look at the sample size. We're going to look just at the statistics in its own merit. So in this case, it's 1.43. So in this case, it's 1.43. All right, so now we need to understand what measures of Cohens D are important, which measures are not. That's important. Well, I can tell you for sure that if your Cohens D is over 1, then you really have no issues with sample size, and that's good. Since my D here, my Cohens D is 1.43. Again, my Cohens D is 143. The typical barrier we look for is roughly 0.8. If you're over 0.8, what we get to state is sample size is not an issue. Some people believe if you sample huge amounts of data, you might get a result that rejects just because. Cohens D is a great way of saying, no. Look at my statistic, Cohens D right there, the Cohens D statistic. Right there. It has nothing to do with sample size. It's just about effect. And my number is 1.43. As long as that number is over a 0.8, then what we have is sample size is not an issue. So really on its own merits, my data can stand on its own merits. And so that's good to know. So we often include that at the end if needed, that sample size had no effect or no bearing on my results. Just a note, where's my notes here, my student notes. Cohens D, you can take a snapshot of this. If D is 2.2 or under, we have a small effect size, and so sample size is probably a very potential issue. If D is 0.8 or bigger, we have a large effect size, and so sample size is not an issue. There's this gray area between 0.2 and 0.8 where there is some respects of medium effect size. All right, anything under 0.2, you definitely have an issue. Sample size is driving your answer. You might want to do a restudy. If your D is above a 0.8, you're good. No effect by the sample size. If your D is between these, you might want to write, there is some concerns. Maybe we do a follow-up study just to really make sure my results were not based on the sample size and were based on real results. All right, guys, thank you for watching this video. Stay tuned for more. We'll do more examples of the t-distribution and the t-hypothesis test soon.